Okay, so this section's about dimensions, and we'll talk about dimensions, but what it really means is, well, there's multiple ways to find a basis of a span, right? And depending on what you did, you got a different basis, which kind of makes sense, right? There's multiple different ways to do the foundation because there's not always one particular way you could do one or the other, right? Because there's multiple ways to find the basis. But the key thing is, well, which one's correct, right? And the obvious reason is they're all correct, okay, at some point. But the thing that's actually unique is the number of actual vectors within the basis itself. Okay? Meaning, no matter how many times you do find a basis for a subspace, you're going to have the exact same number of vectors going forward. Okay? And that's what this section is about: is finding the how many dimensions or how much vectors there are actually in that base itself. Okay? So that's where these definitions and corollaries come into play. So let W be a subspace of Rn, and let B be a spanning set of W containing P vectors. Then any set of P plus 1 or more vectors are called linear dependent. Interesting kind of theorem when it comes to it. Basically saying, right, if I have the B is a span for some W, this contains exactly P vectors. If I add one more vector to it, then it's called linear independent. Or sorry, linear dependency. Meaning, I can't add it specifically just for individual ones. Weird kind of theorem. It actually goes down to when it comes to the main definition. So the next corollary is let W be a subspace of Rn. And again, let B be some vectors, all with vectors of 1 through P, to be a basis, and now it's even more, basis for W containing P vectors. Then every basis of W contains exactly P vectors. And that's what I was talking about earlier, is no matter what you do, you can find multiple bases you have, but every basis will have exactly the same number of vectors. Okay? That's what corresponds to this theorem up here. And now we actually the definition to what it is to be, how many vectors we have. So let W be a subspace of Rn. If W is a basis with P vectors, we say that W has a dimension P, meaning the dimension of W is P, where P is the number of vectors within the basis itself. Okay? So a dimension represents how many vectors are within the basis. And again, that means every basis we find for each individual equation will have the same number as well. And that's a key thing going forward. Okay? So let's do a simple little example here. So given the subspace W in Rn defined to be this situation, find a basis for W and find the dimension of W. Okay? So I can rewrite this portion since we have x1 equaling negative 2 x3, and we know that x2 and x3 are the same. So same process. So and our x3 could be any real number. So I could rewrite this to pretty much be this being basically this, right? Or if you want that. Okay? So this means our basis, if I just call it a different letter now, like U, will be negative 2, 1, 1. So this is a basis in W, and since we only have one vector, so the dimension of W would be 1. Now this is kind of a pretty straightforward example. Well, how do we actually want to find the actual basis, right? Like we did last time. So what we're going to do is find it in 3 different ways. Okay, so 3 of the 4 different ways to find bases. Okay, all right. So let W be the subspace with a spanning set of vectors in Rn. Find the basis of W 3 different ways, and then find the dimensions of W. Okay, so the first way is just setting it equal to A, B, C. Or essentially just linear independency. Right, the linear independency way. Okay, so now we just slowly manipulate this down and cross, 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 and eventually we get this matrix. Let me get that. Okay. So therefore, this is only has a solution when this is equal to 0. Or if I just want to solve for one of these letters, so C is defined to be equal to 4A minus 2B. Okay, so that means I have two arbitrary values. So we can so if I want to rewrite this, so C can be written as 104A plus 01 negative 2B, right? So if I want to rewrite that in terms of like a basis format, we'll just let U1 equal to the first one and U2 equal the second one. So there's our basis. And now the dimensions of W would be 2. I think it was W. Yes, W. Okay. So that's the one way. That's one way. And now we're going to show, right, just using the other two ways, we actually do get dimensions of 2. So no matter which way you actually do it, it gives you the same type of vector, or number of vectors. Okay, so the second way is discarding the inconsistent vectors. So I'm going to rewrite what we started with to begin with because I don't want to do all that work again. So what I mean by that is we're going to start here. But remember now these would just be zeros, so all this just goes away. Okay. And now we just simplify this a little bit more, right? Dividing this by 2 gives you 1, 1, and 2/3. And then simplifying this, you cancel this one out. We can do a little bit more to it. So we eventually get this at the very end in the most Euclidean form possible. So we have our pivot points. So remember, this means discarding the inconsistent vectors, and the inconsistent vectors are these two. So x1, x2 are our bases here. So we say u1 is equal to our first vector, which was, if I believe, 1, 1, 2. And our u2 would be our second vector, which I believe is 2, 4, 0. Yep, there we go. So this is our basis. But again, dimension 2. Okay. And finally, the last way is probably the longest way, is using the transpose way. Okay. So remember what that means is we first start again from the very beginning. Then we take the transpose of this. Solve for this normally. And eventually, after solving, everything cancels, which is really, really nice. And remember, according to our theorem, this is equal to B transpose, right? These are equivalent to each other. I'm sorry, these two, because this is W transpose. And now I can revert this to get B again. And again, these don't count because they're zeros. So again, for our basis, we'll let U1 equal 104, which is ironically the same basis we get above. And our second vector is 0, 1, negative 2. So here's our basis for that. Again, still dimension 2. Okay, so again, 3 different ways to find bases. As you notice, not all, it just so happened that these 2 end up being the same, but it could be a possibility that all 3 are different. But again, the dimension will still be the same no matter what. That's the nice thing about it. All right, so based off that, we can go to a little bit more further explanations when it comes to dimensions. And we have a very interesting theorem here. It says, let W be a subspace of Rn with dimension P. And all 4 of these are going to be equivalent to each other. So any set of P plus 1 or more vectors in W is, again, linear independency. So we talked about that earlier, right? 2, any set of fewer than P vectors is all vectors in W does not span W. This is one that's also special. So it's uniquely P, right? So if you have again, so for example, back over here, if we found a basis, or actually so if we just take one of these out and just have, dimensions 1, so it doesn't span the entire W. That would be a big no-no. However, if I add another vector here, let's make it dimension 3, right, which is what this represents here, there will also be linear dependency, meaning it won't be an actual basis. Okay. And then the last 2 represent actual independency. So any set of P linear independent vectors in W is a basis for W, and that's what we proved, right? So these are all linear independent of each other, hence they are bases of W, right? 3 different ways, eventually, but 2 different types of bases respectively. Okay. And then finally, number 4, any set of P vectors that span W is a basis of W. And that's an interesting one there. Okay. All right, so this proof is a little out there, obscure. So I'm going to try my best to explain what it is. So we're going to do number 3. So any set of P linear independent vectors in W is a basis for W. Okay, so this one is a little bit more layout-y than the rest of them. It's just solving for matrices, multiplication, and addition. So we're going to let this set of vectors, U1, U2, all the way to UP, so these set of P vectors, be a set of P linearly independent vectors in W, because we're still in W. Okay. All right. We're also going to let V be a vector in W. Okay, so by definition, if vector V is in W, therefore, based off the definition of linear independency, I can create a equation that has a linear combination of it. So in other words, A naught B plus A1 U1 plus A2 U2, right, plus dot, 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 all the way to AP UP equal 0. So now what we're going to do is we're going to solve for vector V. So that means just bringing all of this over, right, subtracting every single number, and then dividing by A naught, which is just a constant. So therefore, vector V is equal to all of these. So I'm just going to pop out the negative because it's just going to be negative everything, and it's going to be now itself. All divided by A naught. Okay. Well, remember, this is just a constant term, right? So if I divide every single term by this, right, meaning I can split up the fraction because of addition, right? So if I do this divided by this, that divided by that, and so forth on the line, well, it's still just a constant in front of U1, U2, and U2, U3. So that means vector V is a linear combination of the span of U. So all of these. Well, by definition, if it's a linear combination of the entire span, therefore it's also a basis. And there we go. Bit of an obscure one, but interesting one when it comes to these type of proofs now. How connection with linear independency and dependency with when a matrices formats itself. Okay, so a little bit, very theoretical. So let's go back to the actual applications of this. All right, so now that we know dimensions and the definitions of dimensions, we can write a couple things more based on what we have. So the last part goes on to dimensions of something, the null space and the range of the matrix. So the dimensions of the null space of A is called the nullity of A. So this basically means it's the dimension of the null space of A, denoted that way if you want to call it. And the dimensions of the range of A, of matrix A, is called the rank of A. So the rank of A is the dimensions of the range of A. So, those are so special they call them actually something different. That's a key thing. Okay. Right. So again, nullity is the dimensions of the null space. The rank of A is the dimensions of the range of A. Okay. So just be aware about that kind of notation going forward. So now that we have a definition of those two, let's actually apply it. So let's find the rank, nullity, and the dimensions of the row space of A. So this is also a very special one here too. Okay. So again, remember, this means dimensions of the range, and this means the dimensions of the null space of A. All right, so let's do the most work first. Let's do the rank of A. So that means we got to find the range of A first, right? Okay, so that means we just set them equal to, well, we'll just do it a different way. How about that? Just for fun. Okay, so well, since we only want the rank of A, actually, we don't even have to find the range of A. I forgot about that. We just care about how many matrices actually given to us. So we'll do one of the basis formats, right? So we'll do a transpose. So this is going to be A, so we'll do A transpose. I was about to do more work than I needed to, because we actually need to find the rank of A, just the dimensions of it. Okay. So breaking this all the way down, we end up getting something like this, which equals B transpose. So again, using that theorem and then reverting it. So therefore B is going to equal to 1, 0, 0. Oh yeah, 0, 0, 1. Zeros in the middle, and then that one there. Okay. And then just dividing this out gives you positive anyways, right? So it's not too big of a deal. Okay, so crossing out the zeros, we have 1, 2, 3. So vectors 1, 2, and 4 make the basis of our range of A. So therefore, we have a dimension of our range of A equaling 3. Good. Okay. All right, so now let's do the other ones. So nullity and the dimensions of the row space of A. Okay, so we could do actually that one a little bit together. All right, so null and row space. Okay, start from the beginning. And then this time we're just going to start from here and just breaking it down as much as we can. So remember, since it's the null space, it just equals zeros here, or, you know, I guess I'll just follow that same template. Kind of like that, right? So it doesn't matter if you get multiply or subtract, it's still going to these zeros at the very end. Okay. But eventually, breaking this all the way down, we will get this. There we go. Okay. And now, using the unconstrained variables, so cross this one out. So therefore, again, like here, row 1, row 2, and row 4, so these 4 vectors represent the basis of it. So our dimension of the row space of A will be 3. So check. So 1, 2, 3. Okay. And the best part is this also guarantees a nullity, because that means this is all being constrained, right? So x3 is the one being weirded on. So the null is going to be x2, x3, 1 with x3 there. Okay. So therefore our null space of A is any vector v such that v equals x3. Or just like that if you like. So this is only one vector, so the dimension of the null space, the nullity, equals 1. Okay. Right, so interesting fact when it comes to these, and we'll talk about this in a little bit, but for now, 2 theorems. So theorem 1 is if A is an n by n matrix, then the rank of A is equal to the rank of A transpose. Okay? Which means it follows the exact same template. So I kind of use this theorem without actually saying it first, because that's kind of how we did it here. Or not be enough, right? And the next one is if A is an n by n matrix, then the row space and the column space of A have the same dimension. So meaning, if I asked you to find the dimensions of the column space, you would also tell me 3, because we found it to be the row space to be 3 as well. That's the nice thing. So you get a double 1 for 1. Meaning you could find one in the other and you get the same dimension. Okay, it's kind of nice. But for some reason, this is actually not in your book. I just find this a very fascinating, interesting portion, because there actually is a relationship between the rank of A and the nullity of a matrix. Okay, so going back over here, so for the null space of A, we had one vector, right, one dimension, and for our rank of A, we had 3. Okay. Now the question is, well, how many columns do we have in our original matrix? 1, 2, 3, 4. Right? So it's very interesting because, well, what's 1 plus 3? That gives you 4. So again, this is a very special formula connecting nullity and the rank of A, meaning the n value, so the number of columns, is always equal to the rank of A plus the nullity of A. Meaning, if you could find one of these, you already have the rank of the other using that special thing. Again, it only works if for the n one, so the number of columns, not in the rows, number of columns, which is a very interesting one. I'm not really surprised why I don't have that in the book, but I always like showing you guys that's a pretty unique one to go by. Right, we're going to help each other doing this situation here. Okay, so one more thing, we actually do some more examples. One major example, actually, going forward, is these two. So let an n by n system of linear equations equal ax equals b is consistent if and only if the rank of A is equal to the rank of A divided by B, which is a weird one. Okay. And the next one is an n by n matrix is non-singular. We'll talk about that a little bit more later on as well. If non-singular, if and only if the rank of A is n. Again, more things we'll talk about as we go along in this class. These will get more advanced itself, which is interesting when it comes to non-singular, right? Okay. Now, last theorem is very, very interesting. Okay. Well, actually, this is the last theorem. Sorry. So let's talk about this one more because we're going to do an example illustrating this fact here. Okay. All right. So, yeah. So we're going to talk about what it means by non-singular and the rank of A being n. Okay. And we're going to use this theorem to help us use this odd example here. Okay. Now, we want to show that A be an n by n matrix. Okay. Prove the rank of A is less than or equal to m, and the rank of A is less than or equal to n. Okay. Now, this is a bit of an odd situation. Okay. So we'll just go one point, right? So the rank of A is the number, we're just going to write this down just for preference sake, right? Is the number of linear independent columns of A by definition. Okay. So what we're going to do is we're going to let A be again an n by n matrix with a little condition that m is strictly greater than n. So for example, 4 by 3. Okay. So the number of rows is greater than the number of columns, right? Because we have row by column. Okay. Okay. So if this is true, then we have this happening. N, right, the number of columns, is equal to the rank of A plus the nullity of A, like the equation I just gave you. Okay, now if this is true, we have two situations happening. Okay? If the nullity of A equals 0, therefore the rank of A equals n itself, then n equals the rank of A, and then we're done. Okay, well, number 2. If the nullity of A doesn't equal 0 or just greater equal to 1. Well, in that case, well, that guarantees you, if I just subtract this over if you want, that means it's going to be less than this. So then n is greater than that, the rank of A by definition, right? It has to be equal to it. So done. So this proves this. Okay. Now, the other way around isn't so straightforward like this was, I guess. If you want to call this straightforward, right? It's a bit tricky here. Okay, so we're going to go back to our portion. All right, so R of A. So again, this represents the range of A, right? The dimensions of the range of A. Okay. And we know this is a subspace. So of Rn, or sorry, Rm. Yeah, M, yeah. So we know this means that the dimensions of the range of A, which is the rank, right, must be less than M by default. Now, equality doesn't really actually hold. Okay? Now, the reason why this doesn't actually hold is because, well, it only holds, so I'll write this down for you guys. Equality only holds if m is less than n, which is kind of weird. Okay. Now, again, why does this hold? Because since at least one column is unconstrained, or inconsistent, sorry. So since we know up here that the rank of A can be less than n, and again, since this is true, therefore it's a possibility this is also true. But again, this only works if this happens, which is odd way of situating, right? Odd way of asking it. Okay. So therefore, we actually disprove something because this is actually an example from the textbook. Really, what this question should say is that the rank of A is less than or equal to the minimum of m and n. That's what it should ask, actually, this. So the funny thing is, this is actually a question in the textbook if you guys want to go into it for a homework question. And we actually just disproved that it should look like this instead. So fun little picture if you guys want to, not everything in the textbook is actually right. So it took me a very, very, very long time to figure out why equality would hold. And I did need a little bit of help. But eventually, I was kind of inspired to state this only, and then it made sense. But really, this is the question that should be asked. So really, we want to prove that the rank of A is less than or equal to the minimum of m and n, and that means it automatically holds no matter what, without this special case there.